Good evening. Thank you for joining. So in week 5, this is an introduction to deep neural network. So in the last week, in the lecture videos, mainly linear regression was discussed. And linear regression, it included taking some input x and then multiplying it with a w or a set of weights w and then finding a y hat, which is the output, and then optimizing the weights by reducing the cost function. So this was what was about linear regression. Now, in logistic regression, you do the same way. You take an input x and then you multiply it with some weights w, and then you get some output z. We can call it z. And then this output is passed through some nonlinearity function so that you can squish the output to values
Madam, screen
between
not
0.
visible.
Sorry.
Screen not visible.
Oh, is the screen not visible?
Not
Then
visible.
for everyone?
Visible, ma'am.
It is visible,
Visible.
visible for me.
Okay, maybe then you need to change your layout, then it will be visible.
Okay, madam.
Okay. Okay. So you take an input x and then multiply it by weights w, and then you get some output called z, and then you pass this z to some nonlinearity, so you can squish the output to a 0, 1 range. Now, we denote this nonlinearity function as g of z. And for logistic regression, we mainly use a nonlinearity function called as sigmoid. So for neural network, we change these steps. So there will be a linear combination, then a nonlinear combination, then a linear combination, followed by a nonlinear combination. So each of this pair of operations is what we call as a layer. So these are all the things that we are going to discuss in today's session. And so as I told, each of this operation that is called as a layer. And when it is a deep, and when we have a deep neural network, it is simply a neural network with more than one layer. Mainly more than one hidden layer, which we will discuss later. This is the introduction to deep neural network. So starting with logistic regression. So logistic regression is the first classification algorithm that we are discussing in this course. So regression, as we have discussed in the last classes, finding some real number value. But logistic regression is not a regression problem, but it is a classification problem. Now, the question is, why can't we use regression itself for classification? The issue is that regression will not give you a bound. It generates a line, but then the issue is sometimes if it generates a point that is very far from the line, we don't know how to classify that. So the best way to do use regression for classification is to use logistic regression. So whatever output you get from regression, you squish it to the 0, 1 range, and then you find the threshold in the 0, 1 range that will help you to classify between two category, either class 0 or class 1. So, so if you try to use linear regression, we'll have y hat is equal to, so, okay, y hat is equal to W0 plus W1 x 1 plus W2 plus x2 plus, okay, let us imagine that we have only two features, x1 and x2. So if we have it will always generate a real value only. So to make it a classification problem, for example, you want to classify between, you have a binary classification where you want to classify the input x1, x2 to either 0 or to 1. So in that case, you use some nonlinearity which can map any real number r into either 0 or to 1. So this is what logistic regression does, and this nonlinearity is what we call as sigmoid, and this is given by this function 1 by 1 plus e raised to minus z. So it ranges between a value, the value of the sigmoid is between 0 and 1. Now, as z tends to infinity, this is the sigmoid of z is denoted as this sigmoid of z. So when z tends to infinity, positive infinity, it will lead to a value of 1. And as z tends to minus infinity, the sigmoid of z will tend to 0. And at z is equal to 0, sigmoid is 0.5. So this you can get from substituting these values here. So when z is equal to infinity, you get 1 by 1 plus e raised to minus infinity. E raised to minus infinity is 0. So it is 1. 1 by 1 plus 0. Now, when z is equal to minus infinity, you get 1 plus e raised to infinity. E raised to infinity is infinity. So 1 by infinity is 0. And then when z is equal to 0, you get 1 plus e raised to 0. And e raised to 0 is 1. So you get 1 by 2, which is 0.5. So this is how we get these values. So it crosses this 0.5. So most of the algorithm uses this 0.5 as the threshold to say that is class 1, and 0 to say this is class, 0.5 below to say that this is class 0. So for example, when this sigmoid of z is equal to 0.99, then it means that we are 99% sure that this belongs to class 1. Now, when the sigmoid of z is equal to 0.01, now that means there is 0.01% chance that it belongs to class 1. So it is class 0. So when sigmoid of z is equal to 0.5, actually at this point, we don't know what this class belongs to. So most of the algorithm, it will tell when the probability is greater than or equal to zero point 0.5, it is class 1, otherwise class 0. So they use this greater than or equal to. So now the cost function that is used in logistic regression is j is equal to minus of y into log of y hat plus 1 minus y into log of 1 minus y hat. So this is the cost function that is optimized for classification, for binary classification into so either class 0 or class 1. Now, when y is equal to, yeah, yeah, so there are other nonlinearities also that maps to 0 and 1 range. But then so logistic function itself means the sigmoid. So logistic is 1 by 1 plus e raised to minus z. Since it uses sigmoid, that is why it is called as logistic regression. Yeah, can you ask the question?
Yeah, ma'am. Good evening. I am asking about the since we are using the uh, logistic regression for binary classification, or it can be used for multi-class classification, because only we are discussing about the three zones, uh, either 0, zero point 0.5 or 1.
So you will come across this later. Actually, there is here I'm talking about binary cross entropy only, which can help you classify binary, like which can help you do binary classification. But then there is something called as cross entropy, which can help you classify multiple classes where classes are greater than two. I think this is explained in the video as well. In the later session, you might have come across multinomial classification and all those. So when we come to that, when we have multiple classes, then I will tell what the cross entropy is. So here what we are discussing is binary cross entropy. So um, when y is equal to 0 and y hat is equal to 1, then so we need so the so in the lecture video, mainly this discussion about uh, the characteristics of cost function is mainly discussed uh, to determine or to explain how to choose a cost function, because uh, when we choose a cost function, it should uh, highly penalize the wrong prediction, and it should not penalize the correct prediction. So that is why this session is discussed, where the professor gives different values of y and y hat and show that j is equal to or it will lead to an infinite value when there is a misclassification. So when you substitute this, you can see that 0 into log of y hat is 1, so log 1 plus 1 minus 0 into 1 minus sorry, 1 log 0, so that is infinity. So that is how it leads to a infinite value. So when there is um, different y and y hat, I mean the y, and when y is not is equal to y hat, it will lead to log 0 in the uh, it will lead to log 0 in the equation for the cost function, and it will lead to high penalty on misclassification. So then in the video, different logic gates are discussed. So how can we use logic gates for classification? Um, so in the case of OR gate, you have two input x1, x2. So logistic regression is used here to classify into 1 and 0. So when we have two inputs x1, x2 and the output is y, so you get 0, 0, 0, 1, 1, 0, 1, 1. And for OR, it is 0, 1, 1, 1. So in equation wise, we can write W0 plus W1 x1 plus W2 x2. And then So this phi hat is W0 plus W1 x1 plus W2 x2. So our W0, W1 and W2, it needs to be determined. But we know that from this set of values that when it is 0, 0, I should get 0. That means in my sigmoid function, this should be some value that is below zero point 0.5. Then only it will get classified um, as a zero class 0. And this should be a positive value so that it gets classified as class 1. So based on this, you see that different values of W are selected. So it's not like there is one unique W0, W1, W2. You can find the large number of solutions for this W0, W1, and W2. So one such valid set of weights I can show. So for x1, x2 is equal to 0, 0. We need the z to be less than 0. That is, this W0 must be a negative value. Then we can take any W0 value, any real value for W0 that will make it negative. So we can take W0 as -1, for example. Now one set of value of W0 is chosen. Now we need to find W1 and W2. So we can simply put one value for W1 and W2 and then try to see if that works. So I put W0 is -1. So it is less than 0. So y hat is less than 0.5. So it will predict 0. Then when 0, 1 is there, z is equal to -1 plus W1 into 0 plus W2 into, so 0, yeah, W2 into 1. So that is plus 2, so 1. Now this is greater than 0. So it will predict 1. Now for 1, 0, z is equal to minus 1 plus 2 plus 0. So it will also predict 1. Then for 1, 1, minus 1 plus 2 plus 2, that is 3, is greater than 0. So it will also predict 1. So we can randomly try some W0, W1, W2 values and then find whether they satisfy the equations or not. Now, another way to do this is using gradient descent. We find the optimal W0, W1, W2 iteratively. And then in the videos, NOR, NAND gates are discussed. So then comes the XOR problem. So this is where the issue is. This is where they discuss why we need multiple layers. So in case of XOR, when we plot those 4 points, 0, 0, 1, 0, 0, 1, 1, 1. When you plot this, this will have a value. So this is my 1, 1, and this is 0, 0. So this will have a value in the XOR gate 1 and this also 1. But this and this has a value of 0. So you cannot draw a line that separates these points into two different classes. So that is why we need multiple layers. So XOR can be expressed as NOR of, if I have x1 and x2 as input, NOR of x1, x2, so this is the function. So this actually include computing. So in the layer 1, we compute the NOR and the AND function. And in the layer 2, we again calculate the NOR function of the output that was given from layer 1. So this intermediate, this layers, these are called as the hidden layers. So there is an input layer and output layer. And in addition to that, we have hidden layers, which does this calculation of NOR and AND in the layer 1 and NOR of those outputs from layer 1 in the layer 2. So this is why we need multiple layers when we can't express a function or when we can't correlate our input x to output y through a simple line, then it becomes a nonlinear function. We need a nonlinear function, and that is so multiple layers is one way to solve this issue of nonlinearity. So then there is this universal approximation theorem. So this means that any mathematical function can be expressed as so with one hidden layer we can express any mathematical function. So this is something that has been proven, and this is but then one issue is that we don't know how many neurons we need in that hidden layer. It could be many, could be even billions. But there is a theoretical guarantee to this theorem. But we don't know how many neurons in that hidden layer. Then in the video, the sigmoid derivative is discussed. The derivative of sigmoid is given by sigmoid of z into 1 minus sigmoid of z. This is this is something that is very handy when we deal with backpropagation, where we calculate the derivatives. So then the gradient of loss function. So we have the loss function j, and we know chain rule. So we have to find the optimal weight. So we find the gradients with respect to the parameters w for this cost function. And this j is, it will be some, I mean, for regression, it was this function. But then for binary cross entropy, it is minus y into so it is like this for the binary cross entropy loss function. Now this is j, and this j is dependent on this y hat, and this y hat is sigmoid of z, and this z is w transpose x. So to find the weights, the optimal weights, to find the gradient with gradient of j with respect to w, we need to first find dou j by dou y, and then dou y by dou z, and then dou z by dou w. So when we do this, this is dou j by dou y. So the derivative is 1 by y hat. So minus y by y hat minus 1 minus y by 1 minus y hat. And then when we do the dou y by dou z, that is sigmoid. So it is y hat into 1 minus y hat, because sigmoid is sigmoid of z into 1 minus sigmoid of z. And when we take the derivative of this, we get x. So when we rearrange this, what we finally get is this y hat minus y into x. And this is the similar same expression that we had for linear regression as well. Now, another thing that was discussed is when we had linear regression, we had a mean square error cost function, and that is a parabola. But in case of binary cross entropy, it is not a parabola that we have. Okay, so now we'll discuss some practice question. What defines a deep neural network is having more than one hidden layer. Yeah, so XOR gate is the one that needs hidden layers and is not linearly separable. Yeah, so what is the primary loss function for binary classification? It is binary cross entropy. So which of the following is true regarding the sigmoid function? It maps values to the range -1, 1. Its derivative is sigmoid into 1 minus sigmoid. It's not a linear function. It's only differentiable at x is equal to 0, not correct. What happens when the sigmoid approaches negative infinity? What happens to sigmoid when x approaches negative infinity? So what happens to sigmoid when x approaches infinity? So it approaches 1, it approaches 0.5, it approaches 0, it is not defined. What happens to sigmoid when x approaches minus infinity? Yeah, so when x becomes minus infinity, it becomes 0. Now, one question on binary cross entropy calculation. Calculate binary cross entropy for a sample where true label is y is 1 and probability is, the predicted probability is 0.7. Options are 0.154, 0.357, 1.204, 0.510. One more question from that. So there are 3 samples and their true values are 1, 1, 0. And prediction is 0.9, 0.9, 0.9. And what is the average binary cross entropy? Yeah, so this is the formula that you have to use. So here you have to take minus 1 by n sigma I from 1 to n 5 times log of p of pi, ith probability, plus 1 minus yi into log of 1 minus pi. Yeah, so entropy generally has this negative sign. It is always minus sigma or minus y log y hat plus 1 minus y into log 1 minus y. It's a natural logarithm. Yeah, so it's just a substitution question. You just have to substitute the values in the formula. So if the initial weights are 0, 0 for two features x1, x2, what is the predicted probability for any input x1, x2? Yeah, for the second question, 0.83 is correct. For this question, what is the answer? Yes, so this is Z is equal to W0. So these are two weights, W1, X1 plus W2, X2. And they mentioned that this is 0 and 0. So what you get as Z is 0. So Z is equal to sigmoid of, sorry, the y hat is equal to sigmoid of Z, and that is given as sigmoid of 0, so it is 0.5. Yeah, but bias is not mentioned. It has mentioned there are two input x1, x2 and 0, 0. So in that case, it is 0.5. So when the initial, so here they have mentioned, they have not mentioned that bias. Usually there will be a bias, but here in the question, they have not mentioned that there is a bias weight, and they have just mentioned x1, x2. So if they have mentioned something like x0, which is always 1, and mentioned a w0, then you can use that in the equation here. Add that here. So with initial weight 0, and y true is 1, what is the BCE loss? So when initial weight is 0, we found that the prediction will be 0.5, and true value is given to be 1. And the formula is y into ln of y hat plus 1 minus y into ln of 1 minus y hat. So you get minus 0.693, but there is always a minus in the front, so it is plus 0.693. We just need to substitute this value over here. It's a direct application of formula, just 1. And this is the natural log that you see in the calculator. So there is input X and also a bias 1, and weights are W0 0.5 and W1 0.5. Then what is the activation using sigmoid? Yeah, so just have to do. So the answer is 0.731. Then you have to find sigmoid of this value. It is 1 by 1 plus e raised to, no, there is something doing. Yeah. So why do we have non-linearities in every neuron? Yeah, so it is to allow the network to learn complex nonlinear pattern. So then multinomial classification is discussed in the lecture video. So we had binary classification where we had class 1 and class 0. But when we have more than two classes, we have this multinomial classification. We have multiple class. So then the first question is, how do we represent these multi classes? So one way to represent them is this one hot vector, if I have three class, I can represent them like this. The one hot vector representation. So it is called one hot because exactly one element it will be having the value 1 and all the others will have the value 0. And then since for binary classification we had sigmoid, but for a multiple class, like for classes greater than for number of classes greater than 2, what do we use as the nonlinearity? One option to use is softmax. So we will see what is softmax. So softmax is uh, so it also tries to keep the sum of all the sum of probabilities of different class to have a value between 0 and 1. Sorry, sum will be 1 and each of the class probability will have a value between 0 and 1. So what it does is, so the formula for softmax is given by e raised to z I divided by e raised to z j sum for j from 1 to k. So we take the so for a specific probability value zi that we got, we take that divided by sum of all the probability, then the probability will get normalized and each class will have some value and sum of those class probability will be equal to 1. So this is how the nonlinearity handled in multi-class classification. And another thing is the loss function that is used. So this is done using categorical cross entropy. And this categorical cross entropy is given by minus sigma over y into ln of y hat over k classes. So there is so for each k class we find the sum of their y into ln of y hat to find this loss function categorical cross entropy. So this is for multinomial classification. And then for multinomial classification, mm, yeah, so the weights for a multinomial classification is when we have, for example, when we have an image of size 60 by 60, and when we flatten that, we get 3600 input features. And if we have three classes, then the number of weights will be this three classes into this 3600 weights plus the bias terms for each of the class. So these are the weight metrics for the multinomial classification. Then there is a short explanation about biological neuron. So I'll check some questions. Let us consider this. So there are three classes. As I mentioned before, class A will be 100, class B will be 00010. So like that it will go. So if class C is there, then what is the one hot encoded representation of it? So what is the one hot encoded representation of class C? Yeah, so that will be 001. Now there are 5 classes A, B, C, D, and E. What is the one hot encoded representation for B? Yeah, so it will be 0100 D. Oh, sorry, I missed one. Maybe you can consider there are only 4 classes. So calculate the softmax probability for class A given these are the scores. Yeah, so you have to do e raised to z a by e raised to z a plus e raised to z b plus e raised to z c. E raised to 2 by e raised to 2 plus e raised to 1 plus e raised to 0. So you get 0.665. So we usually say this logits as the values that we get by calculating this W into X, the output values from the neural network. So these are some real values, and what we have to find is the softmax probability for class 1. So this is class 1, 2, 3. There are 3 classes. What is the softmax for first class? Yeah, so it is 0.665 e raised to 4 by e raised to 4 plus e raised to 3 plus e raised to 2. Yeah, so it is e raised to z. Yeah, so chain rule mainly allows to decompose this complex derivatives into products of simple one. So the sigmoid function is known as linear function, quadratic function, logistic function, cubic function. It's logistic function. Yeah, so it is B minus 0.5 plus 1 into 0.5 plus 1 into 0.5. So it is 0.5. No, that was a issue with the way I have written it. So W0 is the bias and the input is always X0. So usually we assign the x0 as what value is the question. So it is 1. In multinomial classification, if we have 10 classes, how many neurons will be there in the last layer? Yeah, so it will be 10. Yeah, so a fully connected neural network will have all the neurons connected to each other. Last year assignment. So this is something that we have discussed s- that is similar to that one. So one-hotted representation. So you'll be able to do this question. So the categories, there are 4 categories, and one-hot encoding is asked for a specific category, retirement. So then only for retirement you will get a value 1. Similarly, to calculate the softmax probability, you need to take e raised to z by e raised to z value for the three category A, B, and C. And the numerator will contain the e raised to z value for a specific category. So, which of the following is not true about sigmoid function? Its value range is between 0 and 1. It is monotonic. It's not linear in nature, and it is differentiable at every point. There are some true labels given, and there are some predicted probability given. So it's just a direct substitution of the formula. So this is your y, and this is your y hat, or pi here. So you just have to substitute whatever is y 1 into ln of 0.9 plus 1 minus 5 will be 0. So that term will get cancelled. So for the first sample, it is 1 into ln of 0.9. Then there is a summation term. So you have to add it. So 1 into ln of 0.9 plus. For the second term, this will be 0 and this will be there. So 1 into ln of 1 minus 0.2, it will be 0.8. So you have to add it. And so similarly, you have to find for each of this sample and then divide it by minus 1 by n. Similarly, you have to calculate the BCE loss for this one as well. So here you are only given the features and the true label. So first you have to calculate with this W 0 values. The initial weights are 0, 0, 0. And so there is no bias. So you just have to calculate 0 into 0, 0 into 1, 2 into 0. That is your Z value. And then you find sigmoid of Z. So sigmoid of Z is 0.5. So you will get the y hat as 0.5 and the true label as 1. Then once you have the true y hat, then it is similar to this predicted probability, and then you can find it. Yeah, so this is where I made a confusion between this bias and this inputs. Then, so then the activation is asked. So you just have to find the sigmoid of whatever value it is. Yeah, similarly, what is the BC law? So I was trying to frame questions similar to this and show you. So this part we discussed the chain rule, dou J by dou W, and to find that we calculate the derivative of J with respect to Y, and then the derivative of Y with respect to Z, and then Z with respect to the weight that we want to update. So so during the feed forward pass, you calculate what is the y hat, the prediction probability or the prediction, and we already have the y value. And then once we have the y value, we know what is the cost function j, and then we find this j dou j. So we have each weight. So we have different layers, and in each layer we have different weights. So with rest, we don't know what is the value that can optimize this prediction from our neural network. So we need to find the correct W for each of the weight, the correct value for each of the weight. So for that, we find the derivative of the final prediction y hat that is contained in the cost function j with respect to each of this weight. And this is done using this chain rule dou j by dou y into dou y by dou z and dou z by dou w for each of the weight. And this is and based on what we get from this gradient calculation, we update the weight as w minus w is at the iteration k plus 1 or at the layer k plus 1 is uh, wk plus 1 minus alpha times the gradient. So, so this whole process is called as backpropagation, where we update the weights through the chain rule, and then we optimize the value of the W such that our final prediction is more close to the actual value. So this is discussed in the where they show a few layers, and then the last layer dou j by dou w is calculated, and then step by step these gradient calculation is done. So I think since it was similar to this, since this chain rule was already discussed, that is why I didn't discuss it explicitly. But then, yeah, in summary, we actually run the forward pass where we calculate all the activations, and the activation is when we have W times activation is given by W into X. And then we get activation in each of the layer, and then in the final layer we calculate the error, and then we propagate backward. That is, for each layer we compute the error, and the we compute all the gradients with respect to the dou j by dou w, where w is the weight in each of those layer, and then we update the weights with respect to that gradient using the gradient descent rule. Yeah. So for regression, we get a scalar value y, and for binary classification, we have this probability value. So whatever we have discussed, we get this probability value with the logistic regression, and for multinomial classification, we get a not just a probability value, but we get a probability vector where each value or each component in the vector corresponds to the probability of certain class. Um, so this is and then the forward model where we calculate the activation by finding the product of weights with the input, and then we have the loss function, the chain rule, and then based on this we compute the gradients of the cost function with respect to the weights to update the weights in each of the layer. So some of the key things to remember is sigmoid has a value between 0 and 1, and the derivative of sigmoid is sigmoid into 1 minus sigmoid, sigma of z into 1 minus sigma of z. The gradient expression for logistic regression is somewhat similar to the gradient expression for linear regression. And then XOR is not linearly separable, and XOR showed us the example for why we need multiple layers in the neural network. And then universal approximation theorem, any function can be represented by a neural network with one hidden layer, but how many neurons are required in that a hidden layer, we don't know. But then theoretically, it has been shown that it is possible to represent every function with a neural network with one hidden layer. Then in the video, sir talks about logistic regression and linear regression convex function. So logistic regression don't have a convex, it doesn't have a convex curve, but then linear regression, it has a parabolic kind of curve. So it has a convex cos function. So then next class, we'll be using these ideas. So mainly the chain rule, the forward activation calculation, all those. I think if you practice more questions, then you will be comfortable with it. So in the next class, we'll be discussing about convolutional neural network, which is mainly used for processing images. And then also recurrent neural network, which is used for processing sequential data. Yeah, so all this will be discussed in the next class. Yeah, so thank you all for attending today's session. So they usually invites application for the fellowship in the website. So you can check the PMR of website to see the requirements. But then I'm not sure because they stopped the scholarship till cycle 11. Now they have mentioned that they'll start cycle, sorry, PMR of 2. But there is no information yet about PMR of 2. But you can always check the PMRF website to see the requirements.